Right, so a semi-batch reactor is a cross between a batch and CSTR. We've already drawn that earlier, so let's have the flow rate come in and no flows out. So we've got some kind of volumetric flow rate. We'll give that a V naught, even though we could just give it a V since it's the only flow rate. We'll say, it's important to note that there's probably some species in that flow rate coming in. One of the reasons why you want to do something like this semi-batch is to introduce some component in steadily that's likely a reactant of some kind. And so then you have the concentration of that species initially. Inside the reactor, you have a particular volume that is very likely to be subject to change since you're adding volumetric flow rate. And then you've got whatever concentration of species I in the reactor and your net generation terms. So if we go back to the design equation and our terms, I won't always write this out, but for now, let's just keep that there as a reference. What do we have coming in? Well, okay. Remember, all of our units here are moles per time. So if we want to try to figure out what our in here is, we have some kind of molar flow rate. I didn't write it that way. I could have had Fi naught here. But if I want to write it in terms of concentration, which I want to do for this exercise just to make something a little bit more clear, let me go ahead and try to write things in terms of concentration. So you have your volumetric flow rate times your initial concentration coming in. You've got nothing going out. Now, you're in this reactor where everything is still well mixed. And so it doesn't really matter where you are in the reactor, your net generation is the same. And so you can go ahead and multiply this by VR. And now, if we remember that dNi over dt, when we do the substitution to put it in terms of concentration rather than moles, we end up with the product of concentration times the reactor volume. So that's partly why I wanted to have it in terms of concentration, because if I did it in terms of moles, I would have, since we have this term, an accumulation term, I didn't want to end up with a dNi, dt, and an F for I, right? You could have F and N, and you need some way to make those two similar. And so what I've done is use concentration. But what you can see here now is that VR is in a time derivative and might not be able to come out. And that's because VR is often a function of time. Okay, so VR might have a starting volume, and then what's happening is you've got this volumetric flow rate of something being added. Just imagine you're cooking and you have a pot that you put a liter of water into. Maybe you're making pasta and you realized it wasn't enough water. For some reason, you feel like you got to keep adding water in. Now, granted, in that situation that I just described, you might have a rate of evaporation. If you had a situation like that, I don't know, one way to think about that is as an out term. Another way is to, treat it like, okay, maybe you're replenishing to keep it at a constant volume. But it's really more like in the case of evaporation, your system is losing something. Let's not think about it that way. Let's just think about it as you have some water in your pot. It's not evaporating. You need to add more. Started with a liter. You're adding, let's just say you're adding like 100 milliliters every few minutes or every minute. Your volume then is going to be growing. And that's one way to think about what's happening here. And the way it's growing is your volumetric flow rate times time. Because think about it, if you're adding, say, 100 mils every minute, then that's a volumetric flow rate. 100 mil per minute, and the amount of minutes you do it for can help you figure out what your total volume is as a function of time. And so that's what you've got here. You've got VR as a function of time. And what that means, in the case of a semi-batch system, is you've got two differential equations that are coupled. So you've got your differential equation here, and then you've got one that for your generalized bounds, and then you've got one that represents how your volume might be changing. The good news is that you can have sometimes feed can be added to account for volume contraction during the reaction. Volume contraction during the reaction. So, not everything has the same density, and in that case, sorry, this should be a therefore. In that case, VR is not a function of time. Well, that can be nice, because then you don't have this second equation, and you can pull out the VR as it's not changing as a function of time. And so hope for that situation, I guess, if you're working on semi-batch reactor problems. But you can deal more computationally rather than analytically solving these coupled equations if they're not. And now we'll talk about PFRs, plug flow reactors, or the major new wrinkle in our treatment of the generalized balance equation is that the entire reactor volume is no longer at one concentration of species I. So let me try to, I drew a box earlier, but let me try to draw a pipe, and this time I'll draw a pipe with this kind of orientation. Okay, and so you've got stuff going in. So let's look at this system. You've got a volumetric flow rate coming in. So we can think about the molar flow rate of species I. If we wanted to, maybe we can think about concentration, but the molar flow rate might be more useful here. Now you have a volumetric flow rate coming out, and something to note, I'll put this in red, note that it could be different than the volumetric flow rate coming in. And if you're wondering why, just remember some fluids are compressible. So then you've got your flow rate coming out, concentration coming out. Okay, so now if we want to look at how to treat this reactor, we can start with assumptions, but I want to start by just kind of drawing okay, so let's start with some assumptions about this system. We're going to assume that along any of the z-axis, at any z, uniform concentration and temperature. So let me draw something to help note what we're talking about here. So in this cylinder, you've got a z-axis, the axial sort of length of the pipe, and what you might have is a mini volume one of those infinitesimal slices of the pipe, where we can call this a differential slice. That's delta z. Well, let me position it here, delta z, and where you're at this position, let's say that's z, and basically at this position you're at z plus delta z. Now you also have then along this dimension, you have an area, right? Okay, so if you're at any given point along the length of the pipe, so let's say you're here, you have a uniform concentration and temperature. Here you have some other concentration and temperature. And so that's what this is saying. So the implication is neglect radial concentration gradients, no radial diffusion. Things are only moving along the length of the pipe in one direction. So also assume no mixing in the direction of flow. Okay, so yeah, we've got nothing mixing this way, and everything is perfectly well mixed this way. Okay, so then if we continue working with this, we know you got to flow in, you got to flow out. And now when we look at this generalized bounce, well, let's go ahead and keep the integral form here, because we know that one of the major assumptions is that there's no spatial uniformity. And then our accumulation remains what it always is, dni dt, and this might be reasonable a form to keep it in. Well, actually, the convenient thing about a plug flow reactor like a CSTR, I don't know if I included this as one of the assumptions, but it's at steady state, and so at steady state dni dt equals 0. So that's convenient. So now we just have fi naught minus fi plus the integral of ri times dvr over the vr equals 0. So note this time ri is a function of vr. So we can't pull this out. And so we have a few different ways to treat this, and I'm just going to show you what I think the book calls the easy way. Let's do a essentially a material or mole balance on a differential slice like I drew before. So if we have this, well, let me actually make its dimensions seem more like what we had before. We have the Fi in any given slice. We have the whole molar flow rate of species I at that moment coming in, and what we have is a molar flow rate of species I plus an infinitesimally changed and small molar flow rate of species I, and we have this over a differential slice in the direction of z. And so one way that we can treat this mathematically is we can say, okay, well, our fi is now our fi naught, and what we have coming out is fi plus dfi, and then we have because we're looking at just the slice, we're no longer having to necessarily integrate. This is our dvr, and that equals 0. Okay, and so when we look at these terms here, we get the cancellation of our FIs. And so we end up with minus dFi plus Ri times dVr equals 0. And we can rearrange that. And that gives us dFi over dVr equals Ri. And this is our PFR design equation. And we can rearrange it if we want to. I'll just go ahead and draw that here so things are still on the same page. If we were to write dVr equals dFi over Ri, that is equation 3-26 in your textbook. And that concludes our just use of the generalized balance equation for all the reactor types that you'll encounter in this course.